Welcome everyone to Science Society, and of course, a special welcome to you, Christine. And before we start, let me give the audience a brief introduction so they get to know you a little bit better, and then we'll go from there. So, Dr. Christina Dow, she is an associate professor at the University of Waterloo in Canada, and the Canada Research Chair in Glacier Hydrology and Ice Dynamics. And her research brings her to far-flung polar regions where she does field programs where she studies the ice shelves of Terra Nova Bay, Antarctica, to glaciers in the St. Elias Mountains and the Yukon Territory. Dr. Dow, she uses techniques as numerical modeling, field data collection, and geophysics, where she examines the changes occurring to the ice sheets and glaciers and this during this climate change or warming climate. She specialized on water systems that accumulate and meander under glaciers, and their crucial role in the flow speed of the ice above it. And before she was at the University of Waterloo, Christina worked at NASA Goddard Space Flight Center, where she used models and satellite data to examine large lakes that form underneath the Antarctic ice sheet. And she did her PhD at the Swansea University in Wales. And before that, she did her master's at the University of Alberta. And as an undergrad, she was at the physical geography at the University of Edinburgh in Scotland. So it's really an honor having you here, because you're really, an expert in these water systems that are, becoming more and more, I guess, the focus of studying how climate change is contributing to the melting, and that's really important. So I wanted to ask you, how did you discover that you have kind of an affinity for science and that you wanted to become a scientist? Is that something you always wanted to do, or did it come later with a class you took or something like that?
Well, I mean, first of all, thank you for the invite to come and talk about this. It's really nice to be here and be able to share some of these stories. So yeah, I mean, it's I guess everybody has a different journey for how they get into their academic careers. And for me, when I was in high school, I discovered glacial geomorphology, and I thought this was the coolest thing that I'd ever heard of. I mean, it just, in terms of the words, it just sounded so exciting. And growing up in Scotland, there was a lot of remnant glacial materials, so all these moraines and landscapes and beautiful features formed by the glaciers. So I decided in high school I was going to be a glacial geomorphologist. And so I went to university to do physical geography with that goal in mind. And as part of that degree, I got to take a field trip to Iceland when I was in my third year of my undergraduate. And the project that I was given was to physically go onto one of the glaciers in Iceland, called Gigiokul Glacier, and to measure what was happening with the water. So I was given a conductivity meter to measure basically how much material in terms of rock and sediment the water had come in contact with. So if you've got water flowing on top of the glacier, it's not going to come in contact with very much. You'll have very low conductivity. If you've got water flowing under the glacier, it'll come in contact with sediment and have higher conductivity. And I just thought this was the coolest thing ever. I just got to run over this amazing glacier feature and measure all these wonderful things. And we actually discovered that the conductivity of water coming out under the glacier was off the scales. We couldn't understand. We thought the instrument was broken, but it turns out it was because there was a volcano in Iceland that was starting to erupt underneath the ice and coming out of this glacier. Do you remember the was it 2013 when everything shut down over Iceland? All of the flights stopped flying because of all the ash coming out of an eruption. It was that volcano that had started acting up in 2005 when we were measuring this. So, we take credit for being one of the first groups of students who actually knew this was going to happen. Probably should have told somebody, I suppose, in hindsight. But in any case, it got me really hooked onto glacial hydrology. I thought this was an amazing thing, and it just incredible if I could have a job doing this. And so that's really what drove me to pursue it, both in my master's and PhD, and then of course at NASA afterwards. And basically, all of my research is still focused around the role of water on ice sheets and glaciers, underneath ice sheets and glaciers, and then interacting with floating regions in the ocean as well. So ice shelves that are the kind of floating margins of the Antarctic ice sheet.
Well, thank you for this wonderful story. It's really amazing um, opportunities and work you did, and congratulations to like follow this passion and yeah, and doing this work. I think it's so important, but also if you enjoy it so much, it's even better. So that's wonderful to hear. I keep saying these rooms like always give me hope actually, because you hear this wonderful stories like how people got supported, how they got very nice opportunities, and then this wonderful work comes out of it. Yeah, it kind of gives hope. And yeah, and then how did this exact project that we will be discussing here regarding the rivers under the Antarctic ice sheet come about? If you have any kind of, background, peek behind the curtains kind of story, that would be really interesting. Thank you.
Well, what I've been doing over the last, I guess, decade now is running models over the Antarctic ice sheet to find out what's happening with the water. So this has been a technique that I adapted when I was at NASA to apply to the Antarctic, and I've been applying it to different regions. Sort of depending on where interest lies from other people and myself, and what data there are to validate it. And I was in Austin in Texas having a hot dog with a with a famous glaciologist, Martin Siegert, and he hadn't he hadn't realized the extent to which we could use modeling now to really investigate hydrology. And he got really excited when I was telling him the kind of outputs we could produce and the kind of discoveries we could make by running these models. And so a couple of years later, he contacted me to ask whether we could run the model over a particularly understudied part of the Antarctic, so the Weddell region, which is, places that are understudied are very interesting because there's so many things to discover. We don't really know what's driving them. And so he had a thought that maybe the hydrology was playing an important role. And he and his collaborator, Neil Ross, who's at Newcastle University in the UK, they had some geophysical data sets, so mainly from radar, flown over the ice that can bounce all the way through the ice to the base. And so they had some hints that hydrology was doing something interesting, but they really needed the model to try and tie it all together. So that's how we started talking about it. And it's in some ways it's kind of word of mouth within a community like glaciology that people either do some reading or talk at conferences or at meetings to try and find out what the new techniques are and where we can start working together. And this is a nice way to bring together different data sets and different expertise. So I'm really excited that it all worked out.
Well, wonderful that it all worked out. And yeah, thank you so much for giving us this kind of background, or yeah, peek behind the curtain. And yeah, for everyone, the slides are pinned on top of the room, and please feel free to access them. And Christine, the stage is yours. Thank you.
Okay, great. Thank you so much. Well, I thought everybody, well, first of all, thank you for coming to listen, but we'd kind of get started a little bit with, kind of 101 subglacial hydrology, a little bit about how the system works, because I realize that there's very few of us in the world who actually really look into the system, and it's quite different from what you imagine in terms of lakes and rivers on the Earth's surface. You know, you're thinking of similar features, but they've got a kilometer or two of ice on top of them. So the physics that we're dealing with are quite different. So if you want to jump to slide 2, I started with an image here with sources of glacial water. So maybe some of you have seen images of the Greenland ice sheet or alpine glaciers with beautiful rivers. You know, the color is spectacular, like in the picture in the bottom there, because it's really absorbing all the light on top of the white ice surface. So you get this brilliant blue river and lake features. They're really spectacular to work with. And they're very important because what this water does is it accumulates on the surface, it runs over the ice until it finds a crack in the ice, which is called a crevasse. And once it flows into there, then you have processes where the water can enlarge that crevasse then into the ice. And the reason for that is because the water is more dense than the ice, so it's always having a downward pushing force on the tip of that crack. And if you get it in just the right conditions of strain in the ice plus the weight of that water, that crevasse can crack all the way through the ice to the bed. So we're talking, you know, through a kilometre of ice, hundreds of metres, wherever you happen to be. And as soon as you have that link between the surface and the bed, then you can start routing surface water all the way down to the base of the ice where it's resting on top of bedrock or on top of sediment. And at that point, you're starting to look at very restricted systems underneath the ice. So we refer to all the water on the top as superglacial. This is all the rivers and lakes on the top. As soon as it enters the middle of the glacier, it's called englacial water. And then once it gets to the bed, it's called subglacial water. And it's the subglacial water we're really going to be focusing on today. If you're looking at glaciers virtually, you know, anywhere else in the world apart from the Antarctic or really high Arctic, very cold areas, you're going to be looking at all three of these. But in the Antarctic, it's still very cold, even with global warming and general temperature change. There's not actually any water on the surface of the Antarctic, or at least very little of it, for the most part. And so I'll discuss a little bit later about how we get that subglacial water, but this should hopefully give you an idea of the complexity of the systems that we're looking at in terms of glaciers. So if you look at slide 3 now, Subglacial Hydrology 101, of course, in reality, systems all across Earth, you know, underneath glaciers are hugely complex. You're going to have a lot of variability in how water is flowing and what kind of material it's flowing through and the size of bumps that it has to flow past. But when we're modeling and when we're trying to think about this conceptually, it's quite convenient to be able to separate into two different categories. So the categories we use are distributed and channelized. And we tend to think of distributed systems as very inefficient. So it's very difficult for water to flow through these systems. You have it building up in like little cavities underneath the ice and tortuously flowing between these cavities to try and make its way from the interior of the ice to either the margin or to the ocean, wherever your glacier terminates. Now, the important thing about these inefficient distributed systems is that they're very highly pressurized. Because that water doesn't really have anywhere to go, it's very difficult for it to flow. It builds up more and more pressure as it accumulates under the ice, and it can build up enough pressure that it can physically lift the ice up above it. And that's very, very important in terms of flow rate. So that the more that ice is lifted up over a larger region, the faster the ice can flow. And that's very important because the faster ice can flow in the ocean, the more sea level rise we're going to have. So a lot of glaciology is trying to look at what is driving these fast flow rates and how this might change in the future. Now, when we look on the channelized side, these tend to be seen as a lot more efficient systems. And what's happening here is that even in your distributed inefficient system, there will be locations where it's easier for water to flow from one cavity to another. And that means water flowing through there is going to be going a bit faster. That allows it to melt out the ice above it, which makes it even more efficient, which can pull more water through, which melts out more ice. So what we end up doing is basically growing channels underneath the ice. And it's a self-perpetuating process as long as you've got the water supply to do it. And when you can get huge channels, I mean, some of them can be several hundred meters wide. And we have evidence of this even in areas of former ice sheets. So across Canada, you've got eskers, which are showing very large channels or the remnants of them from the former Laurentide ice sheet. So we know that this is a process that happens underneath the ice sheets. Now, the important thing about channels is that because they're so large and so efficient compared to the distributed system, they tend to be a little bit lower pressure. And the reason for that is you've got always a competing element of how fast that water is flowing through the channel, allowing viscous melt. So the friction of the water and the ice allows melt. And then you've got the weight of the ice pushing down on that channel. So those are the competing processes. So in Greenland, for example, you have water getting from the surface to the bed, varying over days, hours, changing all the time. And that changing water rate means those channels are constantly growing and shrinking again, depending on what time of the day you are. But they generally tend to be lower pressure. And as many of you know, water flows from high to low pressure. And so those channels will draw the water out of the inefficient distributed system, removing all that nice kind of high pressure lubricating water, and they end up slowing the ice down. So particularly when we're looking in Greenland, we're interested in whether the channels are going to be big enough to slow the ice down in the future. Is it going to speed up? Is it going to slow down? That's a really important message for trying to figure out, how fast we're going to get sea level rise from changing ice motion. Okay, so if we go to slide 4, I mentioned Iceland earlier, and it's a very nice place for looking at glaciers because you've also got volcanoes. You can't get much more exciting than that. And what we have in Iceland is several situations where you can have eruptions underneath the ice and then very large volumes of water from the volcanic heat that's melting out the ice. You get these big, big floods. So in these images, oh, I've gone to slide 4. I don't know if I said that. In these images, we have a subglacial lake called Grimsvotn. It's in the map on the bottom left of the slide. And on the right-hand side, we've got colour scales where it's getting more red the faster the ice is going. I apologise for any colourblind people. This paper was before people were, or academics were actually paying attention to that. So the faster flow is in red. And you can see from the left to the right slide, it's getting faster and faster. And that's as this very large volume of water is flowing under the glacier. So you can see how much of an impact it has on the flow speed as the water flows underneath the ice. So it's really, really important for ice dynamics. So if we go to slide 5 now, excuse me. On the top, you'll see some more pictures of rivers and lakes that I took when I was working in Greenland for my PhD. And at the bottom, you'll see some pictures of the Antarctic. They're very, very different. We've got lots and lots of water on the surface of Greenland, no water on the surface of the Antarctic. So this is why I've been so interested in Antarctic hydrology. It's a bit of a mystery. It really wasn't thought of very much, a couple of decades ago because people just assumed everything was frozen. So there was no liquid water at the base of the Antarctic. Water had very little role to play in how the ice moved. And that's been changing over the last 20 or 30 years as we're beginning, we're getting more and more satellite data. We're beginning to see true patterns of what's happening in the Antarctic. So today we're going to be talking about the Antarctic. I'll come back at the end and compare the systems again. The Greenland system where we've got all of this water on the surface and our efficient channels, and then Antarctica, which we'll examine just now. So if we go to slide 6, one of the reasons that we know the Antarctic is particularly active in terms of hydrology, even though you wouldn't think it because it's covered in such large volumes of ice, is through satellites looking at the ice surface. So these satellites are flying over the Antarctic. They're pinging down laser signals, and those lasers are showing regions of the ice that are lifting over time and then lowering again. So the same region is lifting up and lowering down. And these have the outline of lakes. And so what this seems to be happening is that water is building up in hollows underneath the ice, and it's building up to such an extent it's lifting the ice up by several meters. That lake then begins to drain and the ice surface starts lowering again. And so this is happening over multiple years. This isn't a very, very rapid process. It's really quite slow when we think about it in comparison to our seasonal changes in Greenland. But there's lots and lots of these lakes that are being found. If you look at the right-hand image on slide 6, we'll see the Antarctic with lots of blue dots and lots of red dots on it. The red dots are lakes that have been detected by radar. So this is flying over the ice and pinging radar signals right through to the base of the ice. If it's very flat and reflective, it's indicating there's a lake there. The blue ones are all the lakes that have been identified as being active, which means they grow and drain over multiple years. Some of these are huge. Some of these are growing by 30 meters. If you can think of, a 30-meter deep lake accumulating over a couple of years, that's a huge volume of water. So we're not even talking tiny little amounts of water under the Antarctic. This is a serious volume of water that's accumulating in these systems. So we certainly know things are happening underneath the Antarctic. It's a good place to look at the mysteries of the subglacial drainage system. So if you go to slide 7, one of the most important things to know is how this water actually gets there. So we've got nothing coming from the surface, and instead all of this water is accumulating between the ice and the rock in situ. So part of that is because of geothermal heat flux. This is the heat coming up from the earth that's warming the ice underneath. And ice is pretty good at insulating. So even if it's minus 50 degrees, I don't know what that is in Fahrenheit, cold, even if it's very, very cold on the surface of the ice, that's not going to translate to the bed because you've got a couple of kilometers of ice that's insulating the base. So you can actually have the bed of the ice is much warmer than the very surface of the ice that's exposed to the atmosphere. And so this geothermal heat can warm the ice at the base enough for it to melt. You add that to friction. And so if any of you are into hockey, you'll know that the sharper your skates are, the faster you can skate. And part of this is because of the weight that you have that's being focused into the blade of your hockey skate is allowing frictional water to form between the skate and the ice. And so that thin layer of water allows you to skate a lot faster. And it's the same with the glacier. The friction of the ice with the rock underneath creates heat, and that heat allows the ice to melt. So on the right hand side, between our geothermal heat flux and our friction, we get our mean basal melt rate. Now this map actually I've put up here is a bit out of date. We've got much better ideas now of the basal melt, and it seems to be quite high near the margins of the Antarctic, where we've got very fast flow rates, and lower in the middle. But the most important thing to note here is that there's melt almost everywhere in the Antarctic. So even though a lot of these places don't have very much melt, so a couple of millimeters a year, the catchments we're talking about are so huge, like the size of Ontario, for example, that all of that water accumulating together into one or two single outlets really can create a lot of volume of water coming out from underneath the Antarctic. Okay, so if we go to slide 8, there's some other evidence that we've had in the past that there are active water systems underneath the Antarctic. So these images I'm showing here are a little bit difficult to get your head around sometimes. So the lighter grey is the ice that's on the land. And the green line is the position where that ice starts floating on the ocean. So that green line is called the grounding line. And the dark grey, which is floating ice, is called an ice shelf. And so what Anne LeBrock and her colleagues were able to do in this paper from 2013 was try and estimate where water is likely to be coming out of the edge of the Antarctic flowing into the ocean, and have a look at what this appears like on the ice shelves. So you'll see here there's a few black arrows that are pointing towards lines on the surface of the ice shelf. Now the convenient thing about ice shelves is that they mimic anything that's happening underneath on their surface, because just like if you've got a cube of ice in your cold afternoon drink, then you'll notice that the ice is about 10% above the liquid line and about 90% below. It's the same deal with an ice shelf. So we've always got 90% of the ice shelf below your ocean level and 10% above. And that means if you start eroding into the base of your ice shelf, then you're going to have a coincident dip on the surface. And that's what these stripes are that you can see the black arrows pointing towards. These are dips on the ice shelf surface, which are due to big erosion features underneath. And the argument here is that channels coming out from underneath the Antarctic are allowing erosion and melt up into the ice shelves and creating these very large channels. Now, these are big features. These are, a few hundred meters wide, up to a couple of kilometers wide in some cases. and 100 meters eroded into the ice shelf. So these are pretty big features to be able to see them on the satellite like this. But this does give us confidence that there is some sort of active drainage system at least making it to the edge of the ocean. So all of this background is kind of the incentive for trying to do the more complex modelling of the basal system in the Antarctic. Now, I'm going to do a little bit of a tangent here. If we go on to slide 9, I just want to talk a little bit more about ice shelves, because when we're talking about their stability in the future, how much they're going to contribute to sea level rise, ice shelves are such a key feature to be able to understand that. They're essentially acting as a belt that's holding on the grounded ice behind it. So the friction of the ice shelves with their kind of surrounding boundaries on the left-hand side of slide 9, you can see all the bright colours of the ice shelves. These are bounded by land and grounded ice on all sides, in most cases. And this friction holds back the grounded ice. If you were to remove all the ice shelves, you would have a huge influx of grounded ice into the ocean and a lot of sea level rise. Even if you just melt the ice shelves a little bit, if they get thinner, they're less good at holding back that grounded ice, and the grounded ice speeds up and we get sea level rise. And the reason this is such a problem is that, as you can see from the middle diagram here, a lot of the bed that the ice is resting on is actually below sea level. Part of that is because of the weight of the ice on top of it. But anywhere in this diagram that you can see blue rather than grey means that it's below sea level. And so, particularly in the western region, that is a big issue. And it's a little bit complicated. Probably don't have enough time to get it into today, but there's an issue called the marine ice sheet instability, which means as your ice sheet is retreating into deeper and deeper areas below sea level, it becomes easier and easier to break up ice shelves and the ice sheet and for warm ocean water to access. So basically, areas below sea level is bad news for grounded Antarctic ice. And we're at a very important tipping point right now where a lot of our grounded ice is sitting just on the very edge of retreating into that deep below sea level region. And the ice shelves are the only thing standing in between us and a huge amount of sea level rise. I mean, we're talking meters, even tens of meters of sea level rise if this process is to get started. And it probably won't take that long, over a few decades. So this is something that glaciologists are super concerned about just now. If we go to slide 10, the reason we're super concerned is because we're seeing ocean warming around the Antarctic, in particular focused in the western side here. So the left of the diagram on the left, so that the pink is bad, basically, that means warming. And if you have a look at the slide on the right, this is showing ice shelf thinning. So red is bad there. So you can see there's a direct connection between the warming ocean water and the amount of ice shelf thinning. And so this is what we don't want to see. We know this is directly linked to climate change, and we're really, really worried, particularly because that West Antarctic region is sitting below sea level. So if we move to slide 11, I'm coming back round to the hydrology side of things now. Up until now, it's really been assumed that the driver of this ice shelf change is essentially the ocean temperature. You warm the ocean temperature, you melt your ice shelves, and you cause instability. And that instability is shown in the diagram on the right of slide 11. Where that West Antarctic region is showing grounding line retreat. So remember, the grounding line is the region between where your ice is grounded and then begins to float into your ice shelf. Any retreat of that is bad news because you're instantly adding to sea level rise as soon as you start floating the ice. And it's also retreating into that much deeper area below sea level, and could start this really runaway effect of ice mass loss into the ocean. So the question is it really just the oceans that are playing a role, or is the subglacial hydrology playing a role as well? So that's something I've been looking at with a lot of my collaborators as well. And we'll get into that when we dive into the contents of the Nature Geoscience paper in a few slides. So just keep this in mind. We're thinking both about the hydrology for what it's doing to the ice speed above. So is it making it speed up or slow down? And is it affecting these grounding lines and ice shelf melt? Those are the two primary questions. Okay, so slide 12, we're changing tack here a little bit. There's, up until the past 10 years, it's been very challenging to try and look at subglacial systems just because of our lack of available models. So our models have improved now to the extent that we can apply hydrology calculations over very large areas, which is required for the Antarctic because there's such huge catchments. And we're getting better and better data to input into our models. So on the left-hand side of slide 12, we have a diagram that's showing the basal melt rate. So this is a little bit updated from the one that was on a few slides ago. You'll see the basal melt rate can be more than 50 millimeters a year. This doesn't sound like very much, but for hydrology in the Antarctic, that is a lot of water, especially if it's all amalgamating towards the margin. You can also see a lot of this melt is concentrated in that really risky West Antarctic region. Excuse me. And on the right-hand side, the beautiful map you see there is basal topography. And anything, again, blue is below sea level, and the kind of greeny brown areas are above sea level. And so both of these products, the basal melt and the bed topography, have been produced due to ice dynamic modeling. So there's ways that you can apply ice dynamic models through inversion, where you can take information we have about the surface of the ice, particularly the velocity, and you run your models and you see what that tells you in terms of how much melt there is at the bottom from friction and geothermal heat, and what the topography must be. So it's a fairly complex process to produce these, but in terms of hydrology modeling, this is great because now we've got two of our biggest unknowns in terms of hydrology. We need to know how much water there is, and we need to know what the bed topography looks like, because this is all hidden by, kilometers of ice. If you go to slide 13, this is sort of schematic of the glacier drainage system model. So this is the model that I've been using over the past 10 years. It was developed by Mauro Werder, who's at ETH in Switzerland. And the nice thing about this model is that it's a finite element 2D system. And so that means you've got all these triangles that are joined together by nodes. And you can change the size of the triangles. So areas that you're particularly interested in, like the grounding line or lakes, for example, you can refine these nodes. So, instead of being a kilometer between nodes, instead you've got 100 meters. Now, of course, you couldn't have something this refined for the whole of the Antarctic, certainly not with our current computing abilities. So you really need to pick and choose where you think it's most important. And of course, we do a lot of testing with our finite element mesh to make sure that we're not influencing our results by having the wrong size of mesh. So in terms of our efficient channels, how these develop is on the element edges. So you're calculating how fast water is flowing between two nodes and how much melt that's going to cause above the channel, allowing it to get bigger, and how much the ice above it is going to compress the channel back inwards. Our distributed system is across our elements, so basically on the triangles itself, and this is telling you, how thick your water is getting on that element, how much pressure that water has, and most importantly, how much exchange there is between those triangular element distributed systems and the channels. So this is key because it means we don't have to tell the models where the channels are. It just grows them naturally. So if there's a distributed system element that has a lot of water flowing through it, then that is going to add into the channel and grow the channel, which will pull more water away from the distributed system. So the whole system is linked together, and it means that we've got ability for our different elements or our different systems in the subglacial hydrology network to communicate with each other and to develop in a coexisting fashion. Okay, so that's the most important things to know about the glacier drainage system. Of course, at the end, I'll be happy to answer any questions you might have about this, along with anything else. If we go into slide 14, I'll just show you the progress that my research group has made so far. So we're doing pretty well at covering a lot of the Antarctic in terms of our hydrology knowledge. So all of the green lines there are outlining catchments that we've modelled that have been published so far. And the blue ones are those that are in progress or currently in review for various journals. So we're getting a good idea of how the whole system works. Of course, the goal is to do the whole system. So that's what I'm going to be working on for the rest of the year, is to try and have an entire Antarctic output for subglacial hydrology, which would be very useful for being able to project into the future. Okay, so now we're going to focus in on the study that I was published in Nature Geoscience in 2022. So if you can go to slide 15, this is showing you where this catchment is. And the Weddell Sea region is, a lot of it is below sea level, as you can see from the map here. Again, the blue regions are below sea level, the green regions are above sea level. So you can see a lot of this area is at risk of this instability that I was discussing earlier. On the right hand side, you can see how big this catchment is in the Antarctic. This is taking up a lot of room. And so, we're somewhat restricted in what we can do in terms of modeling refined areas, just because it's such a large area. But it was important to do the whole thing because it's got such a large volume of ice that can contribute to sea level. So if you were to melt all of it, you'd raise global sea levels by 4.3 meters. You can, we're already having trouble with rising sea levels just from a few centimeters. Can you imagine what would happen if we had 4.3 meters of sea level rise? So this area is also pretty interesting because it's splitting the part of it's coming from the West Antarctic and part of it's coming from the East Antarctic. So in the map, you can see a red line that's dividing the West Antarctic from the East Antarctic. And this line even splits one of our major glaciers, Foundation Ice Stream, which is joined by Academy Glacier. We have some other pretty major systems here. We've got Institute Ice Stream, Muller Ice Stream, and Support Force glaciers. So these are all discharging fairly significant volumes of ice out into the ocean. The light blue line that you can see just above the Muller Ice Stream arrow is the grounding line. And so the ice is flowing from basically the bottom of this map to the top left of this map. And so all of our very active hydrology systems we're looking at are going to be coming out over that light blue grounding line. Okay, so if you want to go to slide 16, I'm now going to show some of the main outputs we got from the modelling of this region. So on slide 16, the main diagram is showing channel discharge. And so this is our big discovery in terms of the length of channels. Now, we knew there were channels coming out, but the assumption was that they were fairly, small in length, maybe a couple of tens of kilometers, primarily because we have a lot of fast flow in the Antarctic, and the assumption is you can't have fast flow if you have channels, because channels should slow the ice flow down. However, what we discovered here was that you can have a channel up to 400 kilometers long. And that's joining together with another channel that's, 200 kilometers long. So these are huge, huge features that are flowing underneath the Antarctic. And that's important because what they're doing is they're efficiently moving water from the interior of the Antarctic right to the margin. So you're talking about lots and lots of water accumulation over that area. And indeed, we see at the very margin there, you have a channel discharge of about 24 cubic meters a second. So it doesn't sound like a huge amount, but given that that's happening every second, every day, every year, this is a lot of fresh water that's pumping out over the grounding line. Now, the second key finding is also shown on this diagram. If you have a look at where the channel is coming out over the grounding line, so that's where it's light blue transitioning into the dark orange colours. Those orange colours are representing ice shelf melt. And this is calculated completely separately using satellite products to try and figure out how much melt there is. So this wasn't our work. This was work that had already published by Sushila Adesmili a couple of years ago. But what we discovered was that our channels are coming out exactly where we have the highest ice shelf melt. And that's really concentrated on these very vulnerable grounding lines. So this is why I had my tangent into why ice shelves are important and why ice shelf melt is important, because this discovery means that up until now, really one of the major drivers of ice shelf melt, i.e. subglacial hydrology, has been ignored. And this can no longer be ignored. It's a really, really important driver. The physics behind this is all to do with the buoyancy of that channelized subglacial water coming out over the grounding line. So It's a little bit warmer than ocean water, but the temperature doesn't really matter. It's how buoyant that water is, because it's fresh water flowing into salt water, and all of the warmer ocean waters that are causing dangerous melt of the ice shelves tend to be sitting quite low in the ocean column. But when that buoyant subglacial water comes out over the grounding line, it can pick up the warm ocean water, bring it right up to the base of the floating ice shelf, and cause really enhanced melt. So you need both together. You need your warm ocean water and your subglacial discharge to cause really, really high levels of melt. And we're talking here 20 meters of melt a year. That's a lot of melt that's happening in your ice shelf and a lot of destabilizing that's going on. If we go to slide 17, you'll see that similar features are happening across the Weddell region. So on the left-hand side, we've got Support Force Glacier. On the right-hand side, you've got Institute Ice Stream and Mueller Ice Stream. All of these have channels, not quite as impressively long as the previous one I was showing you, which is Foundation Ice Stream and Academy Glacier. But all of these channels are again associated with higher melt at the grounding line in terms of ice shelf melt. So there is a link basically everywhere we see concentrated fresh water coming out over the grounding line with that enhanced melt. Now, there's also a link between how much water you've got coming out and how much ice shelf melt there is. This is a bit complicated by the depth of your grounding lines and the availability of warm water. So there's not a one-to-one link, but in terms of a general relationship, we are seeing a correspondence between higher channel discharge and higher ice shelf basal melt. And in other regions, we've seen that this directly contributes to grounding zone retreat or grounding line retreat. We can see the grounding line retreating even up the channel location. It's so on point with where that channel comes out. Okay, on slide 18, we're now going to look at what these channels are doing to the water pressure. So hopefully I've convinced you that subglacial channels, particularly long ones that have a lot of discharge, or those that have a lot of discharge from local melt, are really important for ice shelf melt. Now we're going to talk about how these channels are impacting the pressure. So the argument previously has been in other regions of the world that if you've got such big channels, they should really be slowing the ice down. But what we're finding out is that that's not really the case in the Antarctic. The white dots on the images in slide 18 are showing the channel locations, and the color background is it's called a flotation fraction. So the closer those colors are to brown, to dark colors, the closer that water pressure is to the ice pressure. And the closer that water is able to float the ice above it and allow fast water flow. The more blue colors, it means that the water pressure is a lot lower and the ice is likely to be flowing a lot more slowly. But you see, even where the channels are, we've got very, very dark colors. There seems to be very little reduction in water pressure due to these channels. So that's very, very different from our alpine and our Greenland systems. Now, if you go to 19, what these two diagrams, oh, sorry, I've done something very confusing here. So the upper diagram, the red one with blue bits, is essentially what I was just talking about with water pressure, but reversed in terms of numbers. So effective pressure, what you're interested in is the more blue and light colored areas are the higher water pressure areas, the more red colors are the lower water pressure areas. Sorry that's confusing. On the bottom panel, you'll see the ice velocity down here. And what you'll notice is the faster the ice velocity, the higher the water pressure is going to be. So the lower the effective pressure. So basically, to summarize, we're seeing a very similar relationship that you would normally associate with distributed water flow. That where you've got very high pressure water, you're going to see fast ice flow. And that doesn't seem to be particularly affected by our channels. Now we can look at this a little bit further. If you go to slide 20, we can test this by doing some sensitivity runs with our models. So you can change how easy it is for the channels to conduct water. And if you've got higher conductivity for channels, they'll become larger and more efficient. And so we can check what that does to the water pressure. So on the left-hand side, we have our high channel conductivity run minus our normal run. And you'll see that it does lower the water pressure a little bit. So there is an impact if you've got more efficient channels. is just not very much. We're talking, you know, a couple of percent, if that, for most of the region. It does, however, affect it over a very large region. So we are finding links between our channels and the water pressure system over hundreds and hundreds of kilometers away from the channels. It's just not doing a vast amount. So normally, for example, in Greenland, if you have an efficient channel, you would be dropping the water pressure from 100% of the ice pressure to maybe 40%. Here we're dropping it from 100% of the ice water pressure to 98%. So channels are having an impact, but not very much. We can do the same sensitivity exercise by adding more water into the base of the ice. See what happens if, for example, your frictional water increases, or if at some point we get water from the surface of the ice to the base of the ice. And we'll see there that we are increasing the pressure, but again, not very much. So it looks like the system is, in terms of its dynamics, is semi-stable at the moment. This may change in the future as the shape of the ice changes and, if you get really concentrated water inputs in some areas. But, it's really the melting at the grounding line from the ice shelves that seem to be the most unstable part. This interior dynamic signal seems to be pretty stable. Now, the reason that channels aren't having a vast impact is probably because everything's fairly steady. So we talk about steady state and modeling as a system that doesn't change. Now, the system changes a little bit in the Antarctic because you do have some lakes growing and draining, but generally on a month-to-month or even year-to-year basis, nothing much is changing. So there's plenty of time for that ice pressure to kind of equilibrate with our volume of water flowing through the channels. This is in direct contrast to Greenland, where there's not enough time for the ice to creep into those channels, and so you end up having your low pressure channels. So Greenland is not steady state, but the Antarctic is, or at least near to steady state. And that's why these channels can persist, yet not have a very big impact on the ice pressure overall, or the water pressure overall. Okay, so on to slide 21. It's important with modeling to really check that your outputs are telling you something you can rely on. I mean, models can produce lots of outputs, many of which are wrong, and we know they're wrong because they're unrealistic. But even within the range that are realistic, it is really useful to have an ability to constrain those model outputs. And that's where this collaboration for this paper really came into play, because Martin Siegert and Neil Ross had geophysical data that had been collected from a NASA aircraft, pinging radar down through the ice to the base of the ice. And calculations on this gave us the bed reflectivity. So the more reflective the pings from the radar are, the more likely there is water at the base. It's very, very easy for radar to ping off water because it's nice and flat, whereas a rock, is usually a bit more bumpy and tends to scatter signals back from the radar in all different directions. Now, luckily in the Antarctic, more and more data are being collected from radar systems that are giving us an insight, both into where water is, but also what the actual bed of the ice looks like. On the left, you see the NASA aircraft that's been flying over the Antarctic, but you also now have helicopter-based systems, like this one shown at the University of Texas at Austin, with some collaborations I've been working on there. And so you get a result like you see in the right-hand diagram. So the dots in the figure are where we've got bed echo reflectivity that indicates water. So the more white and yellow the dots, the more likely there is water there. And unfortunately, we couldn't constrain our model enough to get really, really narrow channel output apart from the very, very edge of the grounding line. But you'll see there's a general correspondence between where you get higher reflectivity and where you get our model showing water output. It does look like, if you have a look, there's a couple of yellow dots to the top left, or top right, sorry, of our main channel, which seems like there is a major water flow there that isn't being captured by the models. So we've got one of our channels pretty well constrained, and you can even see how this extends into the ice shelf. There's that ice shelf channel coming out here. But it looks like one of our other ones we could do with a bit better basal topography so that the model actually emulates that. So this is where the geophysics really comes into play for constraining the models. On slide 22, this is a MODIS image, a satellite image showing the surface of the ice. Uh, Again, the bumpy grey areas, the grounded ice, and the more smooth flat one is the floating ice. Our red dots here are three major channels coming out from under this region. And then the yellow squares are a few radar transects that I'll show you on the next slide. But you'll see that there's a correspondence between where our channels are coming out and where some of these nice ice shelf channel stripes are coming out from the margins. So we've got a lot of confidence in where our channels are appearing. And it's nice to have these geophysical data sets to just double check that the model's behaving itself. So in slide 23, you'll see these radar transects. The yellow bars are showing where essentially this corresponds downstream to our subglacial channel outflow. In the actual radargrams, you'll see the kind of bump up. This is where where there's melt up into the floating ice shelf. And in the surface diagrams above, you'll see the corresponding dip in the surface that's showing that hydrostatic balancing. So it's pretty good. We've got a good correspondence with our outflow with ice shelf channels as well. And the interesting thing we found was that these do scale with discharge. So our largest channel outflowing into the ice shelf is producing our largest ice shelf channel. And when we've got less subglacial flow, we've got a slightly smaller ice shelf channel. So there does seem to be a direct correspondence between rate of melt and the volume of water coming out from your grounding line. Okay, slide 24. This is now kind of widening out again to more of the whole Antarctic picture. So we're still quite short of data. We're operating as best we can on what we have. But this diagram here is showing where different radar surveys have been completed. So the purple ones are all from this University of Texas Austin survey through their aircraft and helicopter. And they've done an amazing job at collecting really high concentrated data in different regions. The grey in the background is from the NASA campaigns to collect data, but you'll see there's very big gaps, including actually the region that we're remodeling. And so there's a lot more to be done to really find out what's happening at the bed. And what we're hoping is that we can continue collaborating in the future to try and direct these radar surveys. So if we know there's particularly interesting hydrology features from the modelling, we can see if these surveys can go out and very closely map what's happening at the bed. And that will be very useful for trying to validate the model, but also for finding the most interesting things to look at with the radars. On slide 25, it's not just more data we need, we also need a lot more modelling. Now, what I've been talking about so far is a hydrology model on its own. So there is ice above it, so it does know that there's a couple of kilometers of ice above it because we need that closure rate for our channels. But it's not coupled to the ice. And what I mean by that is you don't have a scenario where, say, you have very high pressure water that allows faster ice flow, and then you can have more melt and more addition into the hydrology system. That would be ideal. But up until now, we haven't had coupled systems. And that's actually changed over the last 6 months. We've finally got around or had the ability to couple subglacial hydrology and ice dynamics together. Now, the diagrams on slide 25 are actually an application of this kind of coupling to a glacier in Greenland, which is so far the only place that this kind of study has been published. And this is showing that you've got your subglacial system on the right, and then on the left, what it's showing is melt rate from these subglacial plumes of water coming out the front and then melting the kind of front edge of the ice or the floating ice in front of the grounding line. And so this is exactly what we need for the Antarctic. We need ice dynamics, so we've got that link between hydrology and ice flow speed, and we need ocean models that'll take into account how much subglacial water is coming out and affecting the ice shelves in the Antarctic. And we're pretty much there. We've got the ice dynamics and the hydrology coupled. Now we're working on coupling the ocean as well. So there's going to be a lot of exciting work coming out about this over the next couple of years. Now, in terms of other data, if you go to slide 26, there's been some amazing collaborations recently in the global landscape in terms of trying to gather glacier data. So I've been talking about Weddell Sea region, but there are some other really key regions in the West Antarctic that are vital for future sea level rise prediction. And one of those is Thwaites Glacier, which you can see here, modelled in terms of channel discharge on the right hand side. But these collaborations have been working over the past few years internationally to try and get as much data as possible from Thwaites Glacier. So that's talking about, I mean, you can see all of these options here on slide 26. There's aircraft doing radar, there's seismics, there's melt measurements underneath on top of the ice shelf, there's GPS measuring velocity, there's boats going to look at bathymetry, there's AUVs, there's so many exciting things happening. A couple of papers just got published in Nature about what's happening at the grounding line, and they sent an AUV underneath the ice shelf in Thwaites Glacier to measure water flow coming out of the grounding line. So this is really the first time that's been achieved and the first time we can test it against what the model's showing. And they found some really interesting stuff where they saw pulses in fresh water coming over the grounding line. Now that's something we don't see in our hydrology models. So it's going to be fascinating to go back and try and figure out exactly what's been happening there. And that's really going to improve everything moving forward as we join together these data and models to get the best possible outputs. Slide 27. I mean, really what you would want when you're trying to look at hydrology system is to tap directly into it. I mean, all of these things I've been talking about so far are looking at it remotely. So either through geophysics or from modeling. What we would love to do is to be able to drill through the ice all the way to the base and put some instruments in. Now this has happened in the Antarctic. There's been a couple of lakes that have been drilled into, and there's an image from one of those lakes on the left hand side of slide 27. Subglacial Lake Whillans, and you know, it's fascinating to see what the data are coming out there and see whether it matches what our idea is of the subglacial system. On the right hand side, I'm cheating a little bit. This is actually my own glacier drill from the Yukon, so very, very different environment to the Antarctic. That one only goes 400 meters though, so if we're going to take it to the Antarctic to drill into the subglacial system, I'm going to need a lot more hose. However, you know, it does give us some insights into subglacial hydrology, even if it's in a very, very different environment to the Antarctic. But the point I'm trying to make here is that, you know, really when we're trying to look at these large systems and channels and lakes and so on, getting access is really important, even though it won't happen in very many places. Okay, so that brings me pretty much to the end now. So if we go to slide 28, this is my summary slide, which is really just a comparison between what we know now about the Antarctic, having done these modelling studies, compared to Greenland, which is, you know, where most of the hydrology has been analysed in terms of ice sheets up until recently. So in the Antarctic, we get channels for hundreds of kilometres, as we discovered recently, whereas in Greenland, you only get channels for tens of kilometres. This is because in Greenland, these channels are driven by seasonal changes in melt, and then they tend to close over winter. Whereas in the Antarctic, it's much more stable, steady state, because it's only driven by in situ water at the base. And that's the second point there. The channels are close to steady state in the Antarctic. There's not very much changing them, apart from the occasional lake drainage. And because of that, the channels don't reduce the pressure much below the ice pressure. It's just a couple of percent. So really, the presence of channels is not preventing ice from flowing rapidly in the Antarctic. In contrast, in Greenland, because these channels are opening and closing all the time with the changing meltwater input, they tend to be lower pressure, and they drag high pressure water from the distributed system and can really very rapidly slow down the ice speed. And so we're going to see very different responses to climate change in Greenland and Antarctic hydrology systems. Now, in both cases, we know that high pressure water is linked with fast ice flow. That seems pretty consistent. And now we know why you can have channels and high pressure water flow in the same location in the Antarctic, so they're not mutually exclusive. We know in the Antarctic that we've got hydrological connections across the catchment. So that means that you can have, you know, a channel 400 kilometers long that's drawing water right from the interior all the way to the margin. I would imagine it's the same in Greenland. We haven't tested this yet, but probably things that happen in different areas of hydrology catchments in Greenland are going to affect other areas. It's not clear the scale over which that happens, though. It's maybe a slightly smaller scale than the Antarctic, but we won't know until we do some modelling to test it. And the most important thing, the most important outcome from this research is that in the Antarctic and in Greenland, the outflow of fresh buoyant water from the subglacial system is directly impacting the melt rates at the grounding line. So in Antarctica, this is in terms of ice shelves. Greenland, that's primarily to do with the front of glaciers. There's not that many ice shelves in Greenland. But in the Antarctic, these ice shelves are so vital for the stability of this ice body that we're really beyond the point now where we can ignore subglacial hydrology. I very strongly argue that models in the future, ice dynamics models, ocean models, really have to take subglacial outflow into account if they're going to correctly estimate how much melt there is of ice shelves and how unstable that's going to make the Antarctic in the future. All right, with that, I will stop and I will happily answer any questions you have.
Well, thank you so much, Christine, for taking us through this research and for giving us, the background information so we can understand it really well. This was really wonderful, and I wanted to comment like. I read that already before the 4.3 meters rise that this would I mean, how much are we like in sea level? So how much did we predict that climate change would be? And this would be really a horrific consequence, right? If the worst would happen and the all this ice would melt. The I mean, it's way worse than we thought, or is that not the case? I was quite shocked with that number.
Unfortunately, that number's only for that particular region, the Antarctic. If we're looking at what's going to happen in the whole Antarctic wide, the numbers get even more scary. And so, I mean, the thing to understand is if you melted the whole thing, the whole of the Antarctic, you'd have something like 66 meters of sea level rise. It's crazy. Luckily, the whole thing isn't going to go. It's very, basically, there's no chance that all of that is going to melt. However, that gives you an idea of the scale we're talking about in terms of ice volume. But if we're looking at the most vulnerable regions, so all of these regions that are below sea level, those are the ones that are going first, they're going fastest, and they're the ones that are really going to cause global sea level rise within the next few hundred years. 4.3 meters is actually quite a conservative estimate in terms of how much sea level rise we're going to get. That's if somehow the system stabilizes or we take our best option in terms of emissions. We could, think of maybe 4 meters over the next 500 years or something like that. The problem is if we go along the trajectory we're at now, we're talking more like 12 to 15 meters. And while this is beginning to be included in IPCC predictions of ice mass loss, there's a lot of things that aren't being taken into account there. So, for example, subglacial hydrology is not discussed in terms of instability in the Antarctic. I'm hoping the next IPCC round will be able to include it because it's really going to speed up how fast these systems start reacting. And we're learning all the time about how unstable these systems are, how fast they're reacting, but things are changing faster than we hoped. So in Thwaites Glacier, the really vulnerable one, the West Antarctic, it really is retreating faster than we hoped it would. And so the next 10, 20 years are going to be very interesting to see what happens with that system. But yeah, I mean, we're going to have to brace ourselves over the next few centuries for really serious sea level rise. And the West Antarctica sheet is a terrifying place.
On those forecasts, I'm wondering if you've seen the preprint from James Hansen from last December, Global Warming in the Pipeline, which takes into account the effects of aerosols, which have been underestimated in how much they are reducing the temperature rise that we see due to the various forcings. And I'm wondering and he's projecting that essentially figures like 8 degrees are what we're essentially locked in for, unless something changes rather radically. So I'm wondering if the kinds of forecasts that you just made factor in those observations. To my knowledge, it hasn't been published yet, but I've read through it. It looks really comprehensive.
That's great to know. I haven't actually seen that myself, so I'll have a look. I'll have a look later today once we're off this call. But that's a terrifying number, 8 degrees. That none of the models we've been running for the Antarctic change in the future have taken into account that kind of temperature change. I mean, it's a complicated system because what's happening is the temperature change is changing wind directions in the Antarctic. It's changing how warm ocean water is brought up to these ice shelves. And so what I'm not sure of is how directly the actual rate of change of temperature is going to affect ocean warming. But the problem we have is that, say, for example, we only do 3 degrees of warming or 4 degrees of warming, then there does seem to be this tipping point in the Antarctic beyond which there's no reversing it. So once your glaciers have retreated off their kind of pinning points right now and are actively, very rapidly retreating into the over deepened regions, you can't stop it. And that's where this kind of 4 meters of sea level rise is seeming really likely. That there doesn't seem to be much physical reason for the ice to stop moving at that point.
So I'm digging up the link. I'll put it in the room chat in a
Great,
few
thank you.
minutes.
I have a question. I was thinking about this the other day. I had heard about a technology where they sort of microwave the upper atmosphere in heating it up, and then it rises, and the clouds are then able to condense and it begin to rain. I wonder if maybe a temporary reprieve for the ice melt would be some sort of a technology that could do that upper atmosphere warming and actually cause it to rain in Antarctica. Of course, that would take moisture out of the air and it would put it on to the surface. I wonder if that would even be feasible, or is this just my mind running away with me?
Well, it's an interesting thought, but unfortunately, Antarctica is the driest desert we have. So there's it's because the air is so cold, it holds virtually zero moisture. The accumulation rate that we have in snow in the Antarctic is very, very low, just because there's nothing really to condense and fall out as precipitation. Now, I'm presuming you meaning it would be good to have snow in the Antarctic, because rain on the Antarctic would be terrible, because at that point you're going to start melting the surface a lot faster. You can,
Yeah.
get more water to the base. You're going to speed up your ice. We don't really know what's going to happen when you get water from the surface to the bed. That's something my group is looking into just now to see whether, like in Greenland, it might slow things down. But really, your driver in the Antarctic is the ocean. So your warming ocean, accessing these ice shelves and accessing interior ice as it starts retreating is the big killer in terms of breaking up this ice and allowing it to go to cause ocean rise. Now, there has been an engineering suggestion about how to deal with this. There is a group that looked at trying to put up some sort of barrier in front of the ice shelves to prevent warm ocean water accessing it. And they did some model runs and showed that you could actually advance your ice shelves instead of retreat them. They can thicken, they can become more of a stabilizing feature. So if we could somehow figure out the engineering to do that and make sure that we're not going to damage ocean ecosystems and so on as we do that, you could technically put a barrier up, but my goodness, it would be expensive. I mean, it's probably less expensive to do that than it is to just deal with sea level rise, but trying to convince governments of that, I imagine, would be very challenging.
Who is associated with that work?
Michael Volovic is the person that comes to mind.
Yes, it would definitely be with snow, trying to make it snow. But so you're saying that the the air down there has such little water in it, anyways, that sort of effect would probably be have unlikely results when it comes to trying to make it snow.
Yeah, I think so. I think you'd find it very difficult to get enough moisture to be able to do that. I mean, of course, if we can increase the snow in the Antarctic, then it will increase the mass. And as your air temperature warms in general, you'll be able to hold more moisture and have more snow. So there will be a slight offset. We will see some mass increase in parts of the Antarctic because of that effect with more snow, but it's severely offset by all of this other stuff happening at the margins. It's you need a lot of snow to try and offset that, and I suspect it takes a while to form glacial ice from snow. It's not an instantaneous effect. So I think probably even if you dumped as much snow as you could on the Antarctic, it's not likely to keep pace with the damage that's happening at the very margins.
Another point that I'll mention, I don't believe it's been published yet, though it was part of his newsletter, December of 2021, if I remember correctly. Hansen was making a relatively strong case that ocean circulation has been stratification has been underestimated in most of the models, and when you replace those values with more realistic ones, the models show get more accurate in a variety of ways, but also show that the amok is attenuating and is in danger of shutting down by around mid-century.
Yeah, that would be pretty bad news. I'm not surprised. I mean, the thing with modeling is it's always a moving target, right? We're always getting better computer power, better ability to make these large scale calculations, and so everything we're doing in terms of ice dynamics, ocean circulation model, subglacial hydrology, we're always trying to make it better and better. And sometimes it's with our current abilities of computing, it's just not possible to get all the physics that we want into the model. And I mean, it tends to seem to be the case that once we get more and more detail in there, that the stories coming out of them seem a bit more and more dire in terms of how fast things are changing. And scientists, you don't want to over predict something. You don't want to say, oh, everything's going to change in the next 10 years, unless you're absolutely sure that it's going to do that. So especially when it comes to modeling for the IPCC and so on, it being a bit more circumspect about timelines has been the tradition. But I think nowadays science is coming around to being a bit more upfront about the speed that things can change. I mean, sometimes it's just our lack of knowledge how fast these systems are reacting, but other times it's trying to be as cautious as possible and as thorough as possible with our model outputs.
Yeah, which is understandable, but leads to a systematic ignorance about tail risks,
Right.
and
Yeah.
it's all in how is the question asked. If the question is how sure are you that this climate change is real and that we've got to make these massive costly changes to our economy, are you absolutely sure that we have to do this? You get one kind of answer. But if you ask the question, okay, how can you be 99% sure that we will avoid civilization disrupting climate change between now and 2040, right? Totally
Mm-hmm.
different questions,
Yeah,
right?
absolutely. But at least we're now in the situation where 99.9% sure that it is human caused. I mean, that tends to not be a conversation anymore, which is really a relief to not have to discuss that anymore. That virtually everybody in the science community and hopefully generally accepts that climate change is a problem. It's just a matter of how fast it's changing and how fast governments are going to have to react to change. But given even just our numbers of forest fires and droughts and storm blizzards. I mean, it's changing so fast in terms of day-to-day life that I think people are beginning to see that actually instead of being a problem for the next generation or 100 years from now, this is something we really have to start dealing with right now.
Yeah, thank you for those questions and those comments. And Eli, thank you for sharing that resource. Denise, did you have a question? I wanted to give you an opportunity to speak.
Thanks, Katerina. Thank you, Christine. This was a really interesting presentation. I was looking at the slides along the way. I was curious on one of the slides it showed autonomous underwater vehicles. I was curious what the mission duration is on those vehicles.
Okay,
As in,
you're
how long
really,
can they be deployed at one time?
yeah,
5
so you're
hours, 10 hours?
testing my my knowledge of what my collaborators are doing. Um, uh,
It's
I
okay
don't,
if you don't know
yeah,
the answer.
no,
It's fine.
I know they can go for multiple hours. They certainly have improved the battery technology to do that, but a lot of the tests so far have been tethered because people are scared of losing their AUVs under the ice, which is, you know, very expensive instruments. So it's only recently they've started actually putting them out for much longer time periods. But if you want to have a look at the latest paper that came out in Nature, it was by Brittany Schmidt, and it was just published, I think, in February of this year. And so their AUV managed a couple of deployments right to the grounding line, which is where the really exciting data are coming from. But yeah, I think we're talking more, you know, less than a day to deploy rather than having them under there for multiple days at a time.
Yeah, I mean, I was thinking that the temperatures, we know that batteries don't do very well in very cold temperatures. Of course, there could be insulation or whatever, but I'll take a look at the supplemental material. I was also curious, what is the most amazing thing that you have learned in all of your frigid studies?
Oh my goodness, that's a very good but difficult question to answer. Most amazing thing. Like I think this connection between the subglacial discharge and the ice shelf melt is by far the most important thing that I've discovered through my work, and I was actually quite shocked by how much of a correspondence there is, and it's not just in the area that I showed you; it's everywhere. Everywhere I've done modeling around the Antarctic, the grounding line retreat, the subglacial channels, and the high ice shelf melt all line up perfectly. It's a really, really constrained process that is, you know, is going to be so vital for figuring out exactly how fast this is going to be happening in the future. And I'm really hoping that the importance of this is being taken aboard by the glaciology community and move forward. So that was, it was a very exciting moment to first discover that.
Yeah, it was really interesting to hear about the hydraulic effect, essentially, of the underground formations and how they can shape the surface dynamics.
Oh, I'm glad you
That
found it
was,
interesting. That's good.
yeah, well, I mean, I took hydrology in college, so this is
Oh,
sort
nice.
of something that's interesting to me in general.
Oh, great.
Um, so how, well, are there any book recommendations that you can give for people who are new to the subject? Because I'm sure, I know there's one person at least in the audience that likes this question.
I mean, books in a field like glaciology are a little bit tricky because the discipline is advancing so fast that, you know, things tend to get out of date quite quickly. So I would actually recommend keeping up with journal articles
Journals,
in
yeah.
Nature, Nature Geoscience, and Science Advances. Those are where the really big discoveries are coming out just now, and where the most exciting new stuff is coming. I mean, for glaciology in general, like Glaciers and Glaciations by Ben and Evans is a very good textbook to kind of understand the basics of what's happening. If you want to get really geeky, you can read The Physics of Glaciers, which is one of my favorites. It's got, you know, a few more equations in there, a little bit more details about the physics, obviously. But again, you know, these are published years ago. They're not taking into account some of these new things. So if you're going to read some books, I think you should also keep up to date with the latest publishings in the high ranking journals as well.
Yeah, the journals is usually the right answer.
Yeah.
And two more questions. So you had noted that we should be pretty worried about the calving off the polar regions. So I was curious what you're doing personally to prepare for the situation.
Oh, well, I'm certainly not buying any oceanfront property, that's for sure. Luckily in Ontario, we're fairly far inland. But it's an interesting question. So I just came off maternity leave. I've got a 11-month-old daughter. And it was something, that I've been thinking about a lot, is how to prepare her for this world that we're moving into, because she's likely to see even more change due to climate warming than I'm going to see in my lifetime. And I'll be honest, I haven't figured out the answer yet. I mean, I think what we need to do is move forward with a combination of trepidation, of knowledge about what's actually going to happen. Like that this isn't going to go away. There's going to be change. We can't turn back now, even if we do follow our best options in terms of carbon. But also, hope that humanity's overcome an awful lot in its existence, and hopefully we'll come up with abilities to at least reduce our carbon outputs, and maybe some engineering to offset some of the problems. But I mean, that's all I can do really, is try and prepare her for what the future might be like.
That was going to be the other question. Well, what do you see in terms of policy to fix this? And you just answered that.
Okay.
So I appreciate all your answers and your presentation.
Great. Thank you so much.
So on that last point, one people are now more interested, even with some trepidation, about various quote geoengineering unquote approaches. I have been looking into solar radiation management. I'm not a fan of what I term hopeful chemical dumping, whether it's iron fertilization in the ocean, or sulfate aerosols in particular, or stratospheric aerosols in general. Although with the latter, you have to ask, well, is it likely to be worse than the likely alternative? And
Mm-hmm.
I'm not so sure that it is actually worse. But what I have devoted some focus to is space-based solar radiation management. I'm trying to coin the term insulation modification as perhaps a less unattractive term, but in a really condensed nutshell, because there have been whole rooms done on this, the idea is positioning structures at Lagrange point 1 between the Earth and the Sun to deflect just enough insulation to counterbalance radiative forcing. And what I'd specifically like to both ask you about and encourage you to think about is whether insulation changes, which nobody's been looking at really to any depth, or almost nobody, could be incorporated in the kind of models that you have been doing.
Okay, it's an interesting prospect. I mean, it's like all of these geoengineering situations. The problem is if we mess with something that we don't really know what the downstream effects are going to be. So we know that we could lower the average temperature in the Earth by reducing the amount of sun coming in, but what is that lack of sunlight going to do for other aspects like plant growth and so on? I'm absolutely no expert in that at all. I mean, you could certainly plug that into the models in terms of finding out how that would reduce the global temperature effect and incoming solar radiation. I don't know if that's been tried yet. I don't know if people have experimented with that in the global climate models. In terms of glacial models, we tend to just take the outputs of what the climate modelers have given us. So there's a bit of disconnect sometimes between the different communities in who's testing what in terms of these scenarios. But have you ever read the Mars trilogy? Red Mars, Blue Mars, Green Mars?
No, I've discussed it with people though, but I know what you're talking about.
Yeah, I believe they tried that. I'm not sure it actually worked very well in terms of outcomes for Earth. But also, bizarrely, I think, when were they written? The 80s? They actually had the collapse of the West Antarctic ice sheet was the big problem on Earth, which caused a lot of people to move to Mars. So it's a bit of a um, predictive book there, potentially. Um, yeah, it's geoengineering is really tricky. Like we really, our first option, our easiest option, is to reduce the amount of carbon we're putting into the atmosphere. That should absolutely be what we're trying to do. The amount of methane, all these other greenhouse gases as well. Like we can't rely on technology to save us. This has to be part of a process of becoming a more green planet in terms of using renewable resources. I mean, it just economically, as I'm sure people have seen over the last year or so, it makes a lot of sense to switch to solar power and wind power, and I would really encourage people to do that if they can afford to do it. Certainly something I'm going to do in the future as well, is switch over to solar panel power. But in terms of geoengineering, it's technology is advancing fast, but I don't think we're there yet, and I don't think the research has come full circle yet in terms of iron seeding or atmospheric seeding to really apply that properly. There was a news article out today, I believe, about a new carbon capture outfit in Switzerland, which say that they've managed to do it at a fraction of the power expenditure, which could be a game changer. If we can actually pull carbon out, CO2 out the atmosphere without spending more energy to actually do that, I mean, that's the problem. It takes as much energy to pull it out. So you're just basically not making any change. But if you can pull it out without expending as much energy, then we might have a situation where we can start reducing the amount of CO2 in the atmosphere. But I think we're still decades away from having the technology to really apply any of this. And goodness knows what we need to put something in space
Well,
to block insulation.
actually, that's been the long-standing view. I've run some calculations, and it is actually much more feasible than people realized, based in part on declining launch costs. Just where they are now, not where they're projected to be in the future. But it just thinking about a 40 nanometer thin aluminum foil layer and the attenuation that that can cause and the mass that that takes and the launch cost to get it to geosynchronous transfer orbit and from there to solar sail. There's been a paper on that. Solar sail to Lagrange point 1. That would come out well under $1 per mitigating a ton of CO2 equivalent forcing. And chances are that is a massively conservative figure. Though I will circle back and wholeheartedly agree that this is not, you know, in any way an excuse or a reprieve from having to get off of fossil fuels and to not pollute and
Right.
to run on renewable energies and all the rest. And I mean, and that's one of the things that comes up with even just carbon dioxide removal. That this is just a techno fix to let business as usual continue, and this is just smoke and mirrors, ultimately somehow orchestrated by the fossil fuel industry. And the fact of the matter is we might be over tipping points, even if we stopped emitting everything other than what we exhale yesterday, right?
Yeah.
But we do absolutely also need carbon dioxide removal as soon as possible to reverse ocean acidification, which by itself is an ecological catastrophe that we don't hear nearly enough about. And
Yeah.
there's only so much bandwidth and it's taken up by climate, rightly. But there's a lot that we have to do to fix the planet. But the thing is that advanced technologies can scale differently than previous approaches. And I got into looking at space-based solar radiation management just basically on this concern that the type of ocean-based carbon dioxide removal that I've been planning to develop based on phytoplankton in closed photobioreactors deployed in the ocean, which can scale to over 100 gigaton CDR per year by 2030 if we were to pursue it aggressively. you know, if we've gone over tipping points, that's well and good, right? But we're
Hmm.
screwed, right? And so having something that can be deployed in an even shorter period of time to mitigate both against the extremes that are being driven by radiative forcing, but also as an insurance policy against these poorly characterized tipping points. We will only know with certainty once we've gone over them. Let's not do that experiment, has been my attitude.
Yeah, and hopefully we're not too far past it now, for it to make all the difference that it needs to. But that's super interesting. Like, I'll keep an eye out on what's coming out of that, because it's certainly, I hadn't heard about that before, and this idea of putting something into space to block solar radiation, or at least not in terms of an actual real plan. Like, I think as a pipe dream, I've heard of it, but
We're coalescing it, and you know, people in the field, there's a tiny literature on that, you know, have been
mm-hmm.
projecting, well, maybe we can start deploying it by 2040 and get it, you know, full scale by 2060. It's like, yeah, that's game over
Yeah.
if we haven't solved the problem by then. You know, like I said, that figure was based on current day figures, and no huge advances, and there's a chance that it could be tenfold or 100-fold lower, and you know, if we can look to that in a longer term than a short period, with hopefully something more like calcium carbonate aerosols, though
Mm-hmm.
I don't like them. But again, if it's avoiding tipping points, and of course we need to understand everything involved much better, then that's a pathway for getting towards, you know, the 99.9% chance of assuring that, you know, by the end of the century we still have the climate and ecology that humanity has evolved in, right, as opposed to something radically different.
Yeah, just to slow down the change, even if it won't completely stop it. Yeah. Well, fingers crossed. I mean, it's always uh, it's always the hope, right, that something's going to work to try and at least make the planet habitable for a long time to come.
And I
But
just,
there's so much work to be done.
yeah, and I just want to quickly mention I did find the link to the Hansen newsletter, so that's also in the room chat.
Oh, great! Thank you for that.
Well, Christine, and everyone, thank you so much. I wanted to give you an opportunity to get rid of us because we've been going on for an hour and a half, so you might have other things to do. So I wanted to make sure that we don't overstretch your patience. So yeah, I don't know if you have a few minutes, or we can also close the room now because you've been talking for a long time.
I have a couple of minutes left. I have a student meeting in a few minutes, so
Oh
I
yeah,
probably
then let's
shouldn't.
let.
He's modeling a different part of the Antarctic, but it's very important as well, so I shouldn't abandon him completely.
Yeah, sure. Well, thank you so much for explaining your discoveries that are really important, and we wish you all the best for future discoveries, and stay warm in your must be very beautiful and very different to do the field research.
Hmm.
And yeah, we are looking forward to following your work, and yeah, to hear what comes out of your models with the exciting new data merging, basically, that you described in the end. I'm really looking forward to that. And yeah, thank you so much.
Well, thank you for inviting me. This has been really fun, and thanks for the questions as well. It's really nice to chat to people about these things.
Well, great. That's the best part. If you, the speaker, enjoyed it too, that's the best scenario. And yeah, thank you so much, everyone. I wish you all a happy weekend. We'll have a room again next week. Um, how we have a neuroscience room, how efficient learning in children changes kind of the GABA, so the inhibitory neural system in the brain, and how it's taking part in learning. And we'll have more interesting rooms coming up, so just follow the club. And Christine, thank you again. It was such an honor having you here, that you took time to talk with us, and enjoy your weekend. Thank you.
Oh, you're very welcome. Thank you so much.
Okay.
Fascinating talk. Thank you.
Yeah, thank you, Eli, for all the resources that you shared tonight. And I'll close the room in 3, 2, 1. Bye, everyone. Thank you.